Hello everyone and welcome to the PhD trial lecture presentation. Today we'll be looking at the modeling and control of offshore wind farms through the window of data-driven dynamical systems. We will begin the presentation by talking about dynamical systems, wind power, and the horizontal axis wind turbine. This introduction section would allow those who are unfamiliar with the domain to fathom the subject matter presented in the subsequent slides. We will look at wind plant models and discuss examples on the data-driven modeling of wind plants. We will then look at wind plant control strategies and see examples from the data-driven control of wind plants. Finally, we will draw conclusions based on the subject matter of the presentation. So, what are dynamical systems? Dynamical systems are systems whose behavior can be expressed by equations of the form that appear on the slide. Here x is the state vector, t is time, u are the control inputs, and beta are the parameters. Here f is called the dynamics of the system. We have been dealing with dynamical systems for hundreds of years. In fact, Newton's second law, force equals mass times acceleration, is the model of a dynamical system. We can use this to predict the trajectory of projectiles, to determine the orbits of planets, and a whole lot more. Traditionally, the first principles approach was used to model dynamical systems, where the constitutive laws of physics and the conservation equations were used to derive, for example, the equations of motion. In fact, the Newtonian, Hamiltonian, and the Lagrangian approaches are all models of reality. They are all very good models, and we have been solving numerous problems using those models. But to address new age problems like the brain, the stock market, the climate, and turbulence, we do not have a set of solid physical laws to base these on, and that is when data-driven dynamical systems enter the picture. From time immemorial, humankind has been gathering and storing data. From the cave paintings to the pictures of the Martian surface by Pathfinder, we are sitting on a heap of data. Ever since the invention of the computers, our ability to store and process this data has been growing at an exponential rate. We now have better algorithms for optimization, better algorithms for identification, machine learning techniques, regression, neural networks, genetic programming, the list is endless. So we are now at a point where we can use the principles of data science to analyze the data that we have regarding a system and derive its dynamics. So data-driven dynamical systems are defined as that branch of science which deals with the identification, characterization, and simulation of dynamical systems solely based on data. Now, what do we want to use these tools for? We want to use these tools to address problems where the dynamics are highly nonlinear, where the dynamics are unknown, where the dynamics are chaotic, where there is significant transient behavior of the system, and where the systems have multi-scale effects. For example, in turbulence, if you keep zooming down into different levels, you still see these turbulent structures. We would like to address problems that have a high dimensionality of the state vector and problems that have uncertainty in the system parameters. Why do we want to do that? We want to do that so that we can predict the future state of the system, for example, as in climate prediction, to optimize the design, for example, optimization of the wind plant design, to develop control strategies for such systems, and to improve our interpretability and intuition of the system. The techniques used are regression, neural networks, deep learning, genetic programming. Again, the list is not exhaustive and new methods keep cropping up every day. Let's put data aside for some time and talk about wind power. Why wind power? The obvious answers are reduced carbon emissions, reduced energy import costs, especially for countries that are deficient in fossil fuel reserves. And wind power is a fairly mature technology and there are not many technical constraints to be overcome. The only limitations seem to be regarding location, especially in countries where land is at a premium like the Netherlands, you do not have space to install these wind turbines. So what can you do in such scenarios? Well, you can group together the wind turbines to form wind farms and reduce the overall footprint. This has the added advantage that there are reduced installation, commissioning, operational and maintenance costs. You can also move the turbines or the whole wind farm offshore, but these measures have their own associated limitations. For example, when you move the wind farm offshore, then there is a 60% increase in the power produced, the cost of the power produced. And when you group together the turbines to form a wind farm, then there are aerodynamic interaction effects that reduce the efficiency of the wind farm. The cost increase is an economic decision, whereas the aerodynamic interaction can be reduced by plant optimization and using proper control strategies. And this is going to be an important topic of our presentation today. Wind turbines come in all shapes and sizes, but usually they are classified into the horizontal axis wind turbine and the vertical axis wind turbine. The vertical axis wind turbine is not very efficient. And so when we talk about wind plants, we are almost always talking about horizontal axis wind turbines. Looking at the horizontal axis wind turbine, we see that there is a rotor and nacelle assembly mounted on top of a support structure. Zooming into the nacelle assembly, we see that the blades attached to the rotor hub. The rotor shaft feeds the input shaft of the gearbox, and the output shaft of the gearbox is coupled to the generator, which converts the kinetic energy of the wind into electrical energy. The pitch angle of the blades can be adjusted, the yaw can be adjusted, and the generator torque can also be controlled, and there is a controller to take care of all that. There is also instrumentation to measure, for example, the wind speed and the wind direction. The power coefficient of the wind turbine tells you the efficiency by which the kinetic energy of the wind is converted to electrical power. The power curve relates the wind speed to the generated power. In the example shown, there are three regions. In the first region, which is below the cut-in wind speed, it is not worthwhile to produce power and the controller shuts down the turbine. In the second region, the objective of the controller is to extract maximum energy from the wind, and so the production curve is brought as close as possible to the maximum production curve by maintaining the power coefficient at CP optimum. In the third region, which is above the rated wind power, the objective of the controller is to minimize the structural and electrical loads to prevent damage. Again, we see that when the wind interacts with the blades, rotor torque is developed, and this rotor torque is passed on to the generator through the drivetrain. The generator converts the kinetic energy of the wind into electrical energy and exerts the reactive generator torque. The generator torque can be set using the controller, and so can the blade pitch angles, and these are then tracked. The power curve shown is a simplified power curve. Usually there are transition regions, for example, to ensure a smooth startup, and control loops to limit fatigue and vibration. Another factor that has to be discussed in relation to wind turbines is the wake. As the turbine extracts energy from the wind, immediately downwind of the wind turbine there is a region where the wind velocity falls. Also, eddies are shed at the tips of the blades, and these eddies increase in intensity. As the wind travels further downstream, because of mixing with the free stream, the velocity deficit recovers and reaches a velocity deficit minimum. The wake is thus characterized by reduced flow velocity, expansion of the wake cross-sectional area, and increased turbulence intensity. The photo shows the wake region of the first row of wind turbines at the Horns Rev offshore wind farm near Denmark. The effect of the wake is not significant for a single turbine, but when you have a power plant like this with turbines placed one behind the other, if the downwind turbine is in the wake region of the upwind turbine, then because of the velocity deficit, the amount of wind kinetic energy available for the downwind turbine reduces, and this results in a lower production by the downwind turbine. Another topic to be discussed in relation to the presentation is that floating wind turbine concepts are still in their demonstrative phases. Most of the offshore wind farms are in shallow water, and all of them are fixed to the seabed using a fixed foundation. And so what are applicable to land-based wind farms are also applicable to offshore wind farms for the purposes of this presentation. So we discussed that there were two approaches to modeling. The first principles model was built up using conservation equations and constitutive laws. The data-driven model was built up using inferences from experiments. A commonly cited example is of a Ph.D. candidate in automotive engineering driving a car. When he is at his office, he uses the first principles to develop the design of the car. But when he is actually driving the car and he sees someone crossing the road, he does not take his pen and paper and start working out the dynamics and then decide when to brake. Also, the first principles model is time consuming to develop. The Ph.D. candidate spent probably 20 plus years studying how to develop this model. The data-driven model is much easier to develop. He went to the driving school and within a few days he learned how to drive the car. The first principles model is very effective and reliable and can be used for a wide range of operating conditions. Again, he can use the first principles model to develop a car, a truck, a bus. The data-driven model is strongly dependent on the data quality. Say you have been driving a car your whole life and suddenly someone gives you a truck to drive, then you will not be able to drive the truck in an optimal way in the beginning because your data quality is low. The first principles model is transparent and can be easily related to physical parameters. The data-driven model is difficult to relate the underlying phenomena. Again, the example is of turbo lag. The Ph.D. candidate, when driving a turbocharged car, can understand why there is a time delay between the pressing of the accelerator and the acceleration pickup. Whereas a person who is not aware of such things, he keeps on wondering why the car is having a delay and he cannot relate to the underlying phenomena. So the advantages of using the first principles model is that you can carry out design through analysis. You have a model before the system is built, and you can use that model to determine the dynamic loads, fatigue, and based on that you can use that to optimize your design and verify controllers. You can use the model for performance monitoring. The disadvantages are that the model needs to be calibrated and tuned. Often there are differences between the actual system that is built in terms of the properties of the materials that were used, in terms of the tolerances, and these can all cause significant differences in the predicted dynamics. The codes are complex in most cases, and because of complexity of the code, only a small fraction of it is verified and even a smaller fraction is validated through experiments. The first principles model is not tailored for model-based synthesis. For real-time control, you need models that are fast so that the controller can adapt to time-varying situations. But if you use a first principles model, then the model takes a longer time to simulate, and so the controller cannot then optimize its actions. Looking at the first principles models of wind turbine, there is OpenFast from National Renewable Energy Laboratories, which has modules for aerodynamics, hydrodynamics, servodynamics, and structural dynamics. Looking at FarmFlow from the Polytechnic University of Madrid, it has a module for aerodynamics. And SOFA, simulation for offshore, onshore wind farm applications, again from NREL, is a fluid dynamics solver based on OpenFOAM coupled with FAST. It also has a supercontroller module which allows for evaluation of control strategies using a supercomputer, but I read that to simulate almost 30 minutes, you need a day. Looking at a random figure from that represents the outputs from a first principles model, we see that the figure represents the hub height velocity field, in fact the velocity deficit. We see the wake effect. There is the near wake region, there is a high velocity deficit. In the far wake region, the velocity deficit recovers. The second figure is for a different wind velocity. Looking at results of a SOFA wind farm simulation, again we see that there are 9 wind turbines, and these are arranged such that the downwind wind turbines are as far away as possible from the wake effects of the upwind wind turbine. Looking at data-driven models for wind plants, there are no packaged data-driven models. Yungo and others proposed a data-driven model for the prediction of wind turbine wakes. Gochman and Geibel presented a data-driven model for short-term power estimation. He and Yang presented a new wake velocity and turbulence model to improve the turbine wake predictions. As an example for data-driven modeling of wind plants, we present the work by King and others, where they present a data-driven machine learning framework for improving the accuracy of lower fidelity wind plant flow models by learning turbulence model corrections based on data from higher fidelity simulations. First, a high-dimensional partial differential equation constraint optimization problem is solved using the gradient-based optimization with adjoints to determine optimal eddy viscosity fields that improve the agreement of a medium fidelity Reynolds average Navier-Stokes model in wind SE software with a large-scale eddy simulation model in SOFA. A machine learning technique using the Gaussian process regression is trained to predict the eddy viscosity field based on RAN's flow field information like velocities, pressures, and their gradients. The Gaussian process is trained on large-scale eddy simulations of a single turbine in SOFA and implemented in a wind plant with 36 turbines. It is observed that the Gaussian process model outputs show improvement over baseline RANS model outputs. Let's have a look at the results. The first row shows the velocity field comparison. The leftmost figure shows the output from the large-scale eddy simulations, which are from SOFA. The middle figure shows the velocity field predicted by the Gaussian process from the RANS model. And the rightmost figure shows the baseline RANS model output of the velocity field. Again, we observe that the Gaussian process predicted velocity field is in better agreement with the higher fidelity LES simulations, with the baseline RANS model actually over-predicting the velocity deficit in the far wake region. The second row compares the eddy viscosity fields. The leftmost figure shows the optimized eddy viscosity field that is the output of the optimization algorithm. The middle figure shows the viscosity field that is predicted by the Gaussian process, and the rightmost figure shows the viscosity field predicted by the baseline RANS model. Again, we see that there is better agreement between the Gaussian process and the optimized eddy viscosity field, with the baseline RANS model actually over predicting the eddy viscosity in the near wake region and under predicting in the far wake region. This Gaussian process was then implemented in a wind plant with 36 turbines, and remember that the Gaussian process was trained using data from a single turbine. Now, when we implement the Gaussian process in the 36 turbine scenario, we see that again the Gaussian process velocities are in good agreement with the large-scale eddy simulation results. The rightmost figure in this case shows the difference between the eddy viscosity fields predicted by the Gaussian process and the baseline RANS model. To understand the significance of these simulations, let's look at the example of a wind plant manager. Say you're the manager of a wind plant and the weather report for tomorrow has just come in. The weather report has values for wind velocities and directions for different times of the day. And your boss calls up and asks you, okay, so how much power do you think we can upload to the grid tomorrow? You would need to base your decision on some kind of a model. If you choose to use the higher fidelity simulation, you can reply to your boss by day after tomorrow. If you choose the RANS model, baseline RANS model, then you risk the chance of over predicting or under predicting the power output. But if you use the Gaussian process in conjunction with the RANS model, then you can provide better estimates to your boss. Another example that we consider for data-driven modeling of wind plants is from Verma and Yang, where they present a data-driven approach to develop a model for benchmarking the performance of a utility scale wind farm. Power curves describe the relation between the input wind speed and the power output, as we discussed earlier. The power curves supplied by the OEMs are ideal, but since the turbine performance degrades over time, you cannot use the same power curve, say, after 5 years. Abnormalities, machine maintenance, and faults make the power curve of each turbine differ from each other. So in this paper, a high-frequency 10-second dataset averaged over 10 minutes across 22 turbines was used for generalization. Outliers were detected and removed for extracting the reference power curve from the average power curve, and the performance of individual wind turbines were then benchmarked against this reference power curve to identify underperforming and overperforming turbines. Let's look at the results. So they averaged the performance of the 22 turbines and got the average power curve. They removed the outliers from the average power curve to get the reference power curve. They then plot the skew and kurtosis of this reference power curve against the skew and kurtosis of the individual turbines, and based on the distance they identify the outliers. When it comes to the data-driven control of wind plants, there are two approaches that are commonly used. One is the data-driven model-based approach, and the other is the direct data-driven optimization approach. In the data-driven model-based approach, there is always a parametric model, and wind plant measurements are then identified to estimate the model parameters, and an observer then updates the state of the model using the estimated model parameters. The optimizer then sends test inputs into this model, and the outputs are analyzed, and the test inputs that produce the best outputs are then sent as control inputs to the actual wind plant. The text just repeats what I said. In the direct data-driven optimization, the measurements are directly used in the optimization algorithm to generate the control inputs. In this case, the efficiency of the optimization algorithm is of importance since the system has to adapt to time varying conditions. Though there is no model included in the scheme, some inherent assumptions about the behavior of the system is used to improve the efficiency of the optimization. Again, the example is of a person who has been driving a car for all his life, going to drive, say, a bulldozer, and if there is someone who tells him that, okay, this is how a bulldozer should be driven, or this is how a bulldozer behaves, and these are what the levers are for, then he can use the data to optimize his approach to driving the bulldozer, and that's what this means. Irrespective of the control strategy used, the aim is to reduce the cost of produced energy. We keep the following considerations in mind. Extracting maximum power from each wind turbine does not always result in maximal output from the wind farm, and so wind farm controllers need to be developed. The wind farm controller makes the wind farm act as a single unit and maximizes power output. If we use the control degrees of freedom to control the velocity deficit, then that's called axial induction based control. And if we use the control degrees of freedom for wake redirection, then it's called wake redirection control. There are two control strategies when it comes to the arrangement of the controllers themselves. There is hierarchical control, where the wind farm controller provides the set point for the supervisory control, which in turn controls the local controller on the wind turbine. In the multivariable control approach, the centralized controller controls all the wind turbines dynamically. As an example of data-driven model-based control, we present the yaw-based optimization control by Gebrard in his Ph.D. thesis, where he presents a data-driven model-based wind plant control strategy that optimizes yaw settings of wind turbines for improved electrical energy production by taking wake redirection effects into account. The optimization controller is based on an internal parametric model FLORIS, which stands for flow redirection and induction in steady state. The FLORIS model predicts the steady state wake locations and effective flow velocities at each turbine and the resulting turbine energy productions. The FLORIS model has a limited number of parameters that are estimated based on turbine electrical power production data. The parametric model developed has parameters that can be identified by fitting predictions of the model to turbine power measurements in an approach that is referred to as gray box system identification. The model uses measurements from wind plants To estimate relevant properties of the inflow into the plant, the model has a relatively simple structure, allowing for quick optimization of turbine electrical energy productions such that it is suited for real-time control using model-based optimization of the control settings. The game theoretic approach is used to perform the optimization of the yaw settings with the objective of maximization of total wind plant power production. The game theoretic approach performs optimization by making random perturbations to the yaw settings and holds the settings as a baseline setting if they yield improvements of the wind plant total power, so as to iteratively find the global maximum of the wind plant power. Let's now have a look at some results presented by Gebrard. Each result has two sections. In the first section, the velocity field simulated in SOFA for greedy yaw settings of the wind turbines are presented, and in the second figure, velocity field due to the optimized yaw settings that we discussed are presented. Greedy yaw settings refer to the fact that the rotor plane is perpendicular to the wind direction, which enables the individual turbine to extract maximum energy from the wind. And the optimized yaw settings are then based on the control inputs using the yaw-based optimization control methodology. In the first case, the wind direction and the longitudinal axis of the wind plant are parallel. We see that in the first case with greedy yaw settings, there is considerable overlap of the wake regions and there is considerable velocity deficit, especially in the downwind wind turbines. But when using the optimized yaw settings, the wakes are redirected from the upwind wind turbines and there is minimal interference and the velocity deficit has also improved. This points to a case where there should be substantial increase in the power production from the whole wind plant. In the second case, the wind and the longitudinal axis of the wind plant makes an angle of 5 degrees. Again, we see that in the greedy yaw setting case, there is still an overlap between the wakes and the associated velocity deficit for the downwind wind turbines. And with the optimized yaw settings, this situation has improved. And this again points to a case where there should be substantial improvements in the wind plant power production due to the optimized yaw settings. The third case, where the wind is inclined to the wind plant longitudinal axis by 10 degrees, we see that even with greedy yaw settings, because of the inclination of the wind, the wakes do not overlap as much and there are not many regions of high velocity deficit. Again, with the optimized yaw settings, we see that even using the optimized yaw settings, the yaw of the turbines have not changed much from the greedy yaw setting case. And so this points to a case where we do not expect significant increases of the wind plant power. Looking at what this means in numbers, we see that with greedy yaw settings, SOFA predicted a power of 6.68 megawatts for the 0 degree case, while Flores predicted 6.34 megawatts. With the optimized yaw settings, SOFA predicted 7.55 megawatts and Flores predicted 7.66. So based on the SOFA predictions, we see that there is a 13% increase when we use the optimized yaw settings. A similar scenario is seen in case of the 5 degree case. But when we come to the 10 degree case, even with greedy yaw settings, SOFA predicted only 10.8 megawatts. And with optimized yaw settings, SOFA predicted 10.91 megawatts. So the increase due to using optimized yaw settings is not much as we had expected in the 10 degree case. Let's look at what it means for the individual turbines. The gray continuous line represents the SOFA calculated power for greedy yaw setting, while the black continuous line gives the SOFA calculated power for the optimized yaw setting. The gray dotted line is the Flores predicted power for greedy yaw setting, and the black dotted line is the Flores predicted power for the optimized yaw setting. Again, we see that for the first row of turbines, the power output using optimized yaw settings is actually below the power output of the greedy yaw setting power output. But when it comes to the second row of turbines, we see that the optimized control power output is slightly better than the greedy control power output. And when it comes to the third row of turbines, we see a better improvement. In this case, the optimized power output is significantly higher than the greedy setting based output. This is because there is no wake interaction, and the velocity deficit has also reduced because of the optimized yaw settings. So for the whole plant, we see that though the power productions from the first row of turbines decreased using the optimized yaw settings, the power production of the total plant has gone up when the optimized yaw settings were used. As an example of the direct data-driven optimization control methodology, we present again a work from Gebrard. Here he presents a direct data-driven wind plant control methodology where the measured data is used to optimize the control parameters of the wind turbine and make the control adaptable to time varying wind conditions without using a predefined model that predicts the effect of each control action. The objective of the optimization is to maximize the total power production of the wind plant in below rated wind conditions. The maximum power point tracking method was chosen to perform the data-driven adaptive control. The MPPT method was made adaptive to time varying wind speeds by modifying the algorithm in such a way that the objective function is the efficiency by which the wind plant converts the wind energy to electrical energy rather than the total power production of the wind plant. The wind plant control also needs to be adaptive to other changes in wind directions, such as changes in the direction and turbulence intensity, and hence it is required that the optimization takes place in a time efficient manner. To this end, gradient based techniques are used to perform the optimization, and the algorithm is designed using a distributed architecture in which the control parameters of the wind turbine are adapted based on information from the nearest downwind wind turbine. Let's look at some of the results from Gebrard. Again, he presents results such that each has two parts. The first part is a short-term simulation of 1.5 hours, and the second part is a long-term simulation, an extension of the first simulation to 120 hours. He presents the results for two variants of the maximum power point tracking algorithm. He benchmarks his results against a game theoretic approach and shows that on the short term, the MPPT and the MPPT based optimization actually converges to the maximum power production of the wind plant faster than the game theoretic approach. But in the long term, the game theoretic approach catches up to the plant maximum. The small circles show the instance at time where the control was updated. Again, for the wind direction, which is inclined at 60 degrees, without retuning the parameters of the MPPT and GT algorithms, we see that again the behavior is almost the same. The MPPT algorithms perform better in the short term, while the GT algorithm converges to the planned maximum. Again, we note that for the GT approach, results from 100 experiments are plotted to show the effect of the randomization. He then presents results for the 60 direction case, a 60 degree case where the parameters are tuned. We see a slight increase in the performance of the MPPT algorithm. Again, the GT method converges to the planned maximum in the long run. He also presents results for variable wind speeds. The first graph shows the incoming wind speed. The second plot shows the comparison between the local based controller power production and the MPPT based control power production. And the third graph shows the percentage increase, say a 4% increase in power. We now look at the modified gradient descent MPPT control developed by Gebrard. Assume a row of wind turbines where Pi represent the turbine power productions and Ai represent the axial induction factor of each turbine. Due to wake interaction between the turbines, a change in Ai associated with the ith turbine would change the power production of the ith turbine and all other turbines downwind of the ith turbine. Since the power production is dependent on the kinetic energy of incoming wind field, and the kinetic energy of the incoming wind field is given by the expression PV, assuming a constant density, the efficiency by which the kinetic energy can be converted to electrical energy can be maximized by solving the optimization problem, where the objective function is the efficiency of the wind turbine. For local optimization, the axial induction factors can be iteratively updated using a gradient descent optimization method, which was suggested by Boyd and Vandenberg. This results in the gradient descent maximum power point tracking control update law, where the small k is the iteration index and the small scalar capital K is the scaling factor for the induction factor. For a real-time data-driven optimization case, the gradients of the objective function can be approximated from past iterations using first-order backward differencing. A difficulty in the above approach is that it takes a substantial amount of time to obtain the gradients of the objective function. That means if we change the axial induction associated with a turbine at an iteration K, because of the large diameter of the turbine blades, which is an average 150 meter, and because of the fact that each turbine is separated by 6 to 8 turbine diameters, by the time we are able to sense the effect of this control update on the performance of this turbine, considerable amount of time has elapsed, and during this time the incoming wind field velocity would have most probably changed. Other wind conditions like wind direction, turbulence intensity might also have changed. And so to make the algorithm adaptive to time varying wind conditions, two changes are made. To overcome the effects of changing wind speed, the delays related to the wind traveling from one turbine to the next are taken into account in the definition of the efficiencies. Say that Tv infinity to I is the time taken for the wind to travel from the point of measurement Xv infinity to Xi, which is the point of the turbine. To compensate for wind traveling delays, the efficiency can be expressed as shown, where the denominator takes into consideration the effect of the delay. Now for changes in wind direction and turbulence intensity, these influence the way in which the power of each turbine is dependent on the control parameters of upstream turbines. A speed of the algorithm is needed for optimization to be able to track these changes. A practical approach is to speed up the optimization scheme by taking into account only the influence of a turbine's control setting on the power of the turbine itself and on the power of the neighboring downstream turbine. This results in the control update scheme, where the gradients of the objective function on the turbine I and the turbine that is immediately downwind of turbine I are only taken into consideration. This approach is quite a good approximation, because in practical cases there is substantial reduction in the wake velocity deficit as the wake travels from one turbine to the next, and the effect of a control setting change is far greater on the nearest turbine than on the downwind turbine, which is further away. And this is how Gebrard modified the MPPT algorithm to make it suitable for quickly varying wind fields. Thus we come to the conclusion of the presentation. We see that we talked about dynamical systems. We talked about the inadequacy of the first principles approach in relation to new world problems. We introduced the concept of the data-driven dynamical systems. We looked at some background information pertaining to the horizontal axis wind turbine. We talked about the data-driven modeling of wind plants, and we discussed two examples. In the first example, the accuracy of the lower fidelity models were improved by using a machine learning algorithm that used labeled data from a higher fidelity simulation, and we saw that it was a Gaussian process that was used, Gaussian process regression that was used. In the second example, we benchmarked the performance of the wind plant by using an averaged reference power curve based on field measurements, and then we compare the performance of the individual turbines against this data-driven model to identify outliers. In the data-driven control of wind plants, again we saw that there are two approaches. There is the data-driven model-based control, for which we presented the example of the yaw-based induction wake redirection control. And for the direct data-driven approach, we presented the axial induction-based control. We also looked at how Gebrard modified the maximum power point tracking algorithm to make it suitable for real-time control. Thus, we conclude that data-based modeling removes the need to tune the model. Data-driven methods are needed to optimize control settings for site-specific ambient conditions. Time efficiency of the control method has to be taken into account in order to enable real-time implementation. Wake propagation delays play a crucial role in data-driven control of wind farms, and wake redirection control is more effective in maximizing the wind plant power output relative to axial induction control. We saw that with the axial induction control, he was able to get increase of up to 4% in the power production, whereas with the wake redirection control, he was able to get up to 13%. These are the references that I have used. Again, the green arrows show the references that I have directly used in the presentation. I would also like to recommend a book for data-driven science and engineering. The book is by Stephen Brendan and Nathan Kutz from the University of Washington. And with that, I come to the close of the presentation. I hope that I was able to improve your knowledge about data-driven dynamical systems and the modeling and control of offshore wind plants by at least a minuscule amount. Thank you for your attention.